Question 7 is from section 3.6, graphing rational functions. For part A, show and label the vertical asymptotes. Remember, on a rational function, the vertical asymptotes come from the denominator, because really what a vertical asymptote is a domain restriction. When you place a vertical asymptote, it says x can't equal this value. So what we need to do is factor the rational expression, particularly the denominator. And the denominator is going to factor into x minus 3 and x minus 1. So what this means is x cannot equal 3 and x cannot equal 1. Those are where you're going to place your vertical asymptotes, because x can't equal those two values. So there's your two vertical asymptotes. Now for part B, show and label the horizontal asymptotes. For rational functions, if you remember, to determine the horizontal asymptote, you have to consider the degree of the numerator compared to the degree of the denominator. Now in this case, the degree in the numerator is degree 1, the denominator is degree 2. Anytime the numerator has a smaller degree than the denominator, then the horizontal asymptote is a 0. The other case, which we talked about, is going back to the original, if the numerator and the denominator, so let's suppose that the numerator was degree 2, x squared plus 2. If that's the case, if they have the same degree, then you look at the leading coefficients and divide them. In this case, it would have been 1 divided by 1, which is 1. So then the horizontal asymptote would be up 1 unit. But for this problem here, since the numerator was degree 1, which is smaller than degree 2, the numerator has smaller degree, so the horizontal asymptote is at 0. Now it says label and not just show. The horizontal asymptote, since it's a horizontal line, has an equation of y equals 0. Vertical lines have equations of x equals, so this vertical line has an equation of x equals 1 and x equals 3. Now, part C, show and label the x and y-intercepts. Remember, to find a y-intercept, you let all of the x's equal 0. So that would leave you with a point 0, 2/3 for the y-intercept. Zero, 2/3 is about right there. To find an x-intercept, you have to let y equal 0. Well, in this case, f of x is really y. So if I let y equal 0, if I want this to equal 0, the only time, and I've mentioned, we've talked about this before, the only time a rational function like this is going to equal 0 is when the numerator itself equals 0. And what makes the numerator equal 0 is when x equals -2. So when x equals -2, then y equals 0. Now for part D, write the domain in interval notation. X can be anything except for +1 and -3. So from from negative infinity to 1, and then from 1 to 3, and then from 3 to infinity. So that's a domain of every real number except for 1 and 3. Now we need to graph the function. So if you recall, graphs like these rational function graphs that have vertical and horizontal asymptotes, If we start in the right side of the graph here, we have really two options. A graph can never cross through a vertical asymptote. So when it gets near a vertical asymptote, it goes up to infinity. But we've got to figure out, is the graph in the top right corner like this? Or is the graph in the bottom right corner like that? So a quick way to tell is to choose a test point on that side of the graph, like x equals 4. We come up here, if I plug in a 4 for all of the x's, 4 plus 2 in the numerator gives me a 6. And then 4 minus 3 is 1, 4 minus 1 is 3, and 1 times 3 is 3, 6 divided by 3 is 2. So the point 4 comma 2 is on the graph. That tells me that piece of the graph looks like that. Now in the middle, this piece, typically, but not always, the middle piece of a rational function like this would look something like that, or maybe it's the other way like that. But that's not going to happen here because we don't have a 0 for it to cross the x-axis. So there's still a piece in the middle. What's going to happen though is it's either going to be, a piece like that or a piece down here like that. So we need to again test a point like positive 2. We got to figure out where the graph is at positive 2. So coming back to the function, now I'm going to plug in a 2. In the numerator, 2 plus 2 is 4. In the denominator, 2 minus 3 is negative 1. 2 minus 1 is 1. Negative 1 times 1 is negative 1. 4 divided by negative 1 is negative 4. That's about right there. And I know the graph isn't going to look like this because there aren't any zeros here or here to allow it to cross through the x-axis. It can't look like that for the same reason there aren't any zeros. So if this one point is below the x-axis in the middle, then all of the points in the middle are below the x-axis. So it needs to turn down and be a parabola facing upside down. Now, here on the left, we have the x and the y-intercept. Those 2 points are connected. And a graph never bounces off a y-axis, it always passes through. And now the graph's getting closer to this vertical asymptote. So it either has to go up to infinity, or it can turn down to negative infinity. But that last option is not going to work because there's not a 0 right there to have it go through the x-axis. So the graph, when it gets near that vertical asymptote, goes up to positive infinity. Now here, this one's kind of a little peculiar. This 0 of x equals negative 2, the graph does cross through, but then the horizontal asymptote that's right here at 0, the horizontal asymptote is there to show where the graph is when x approaches negative infinity. So the graph isn't just going to keep going down like that. This graph, remember on the sides, on the far right side and the far left side of these graphs, the graph has to scoot along the horizontal asymptote. So it's going to come down and then just continue to scoot underneath and get closer and closer to that horizontal asymptote. Okay, question 8. Now we're in chapter 4. And logarithms, we started talking about in section 4.3. So this right here, log base 2 of x, a typical logarithm function with no transformations has a vertical asymptote right there through 0. Because remember, you can't take the logarithm of anything that's negative. So that vertical asymptote just means the whole graph is going to be here on the right side where we have positive x values. And then there's a point of 1, 0. And the logarithm graph looks something like that. So what we need to do now is apply these transformations, +4 and a +1. We need to apply those transformations to that graph. So this +4, since it's inside the logarithm, it's a horizontal transformation. It's going to move the graph to the left 4 units. So if the whole graph is moving to the left 4 units, that also means the vertical asymptote moves to the left 4 units. So now it's going to be here. At -4. Now this point right there was at the point 1, 0. That's also going to move to the left 4 units. So now it's going to be at, well, actually there's a transformation I'm forgetting about. There's that +1. Now the +1 moves the graph up. That's not going to affect the location of the vertical asymptote, but it is going to affect the location of that point. Not only does it move 4 units to the left because of that, that point also moves up 1 unit because of that transformation. So the point's actually -3, 1. So if I were to draw a table of values, I've got a point of -3, 1. Now, if I were to plug in 0 for x, now I'm not just choosing random values, even though 0 is often a nice number to use. I chose 0 specifically because when you add 4, then obviously you're going to get 4. And the log base 2 of 4 is the same thing as the log base 2 of 2 squared. And remember, the log base 2 cancels the base of 2. So the log base 2 of 4 is 2. And then 2 plus the 1 there is 3. So I've got a point 0, 3 on the graph. So it looks something like that. Now the domain, since the vertical asymptote is here at -4, you aren't going to have any values of x less than -4. So the domain is going to be -4 to infinity. And notice I put a parenthesis around -4 because it's never going to actually equal -4. The range, you can tell by the graph, here it goes down to -infinity. And on the right side, it's going to continue to go up and up and up here, eventually to positive infinity. So the range is -infinity to infinity. Okay, question 9 is still from chapter 4. Now we're graphing an exponential function. This f of x is 2 to the power of x. That's an exponential growth function. It has no transformations. So its graph, if you remember, exponential functions have a horizontal asymptote. And with no transformations, the horizontal asymptote is right there at 0. And then since this is a growth function, it's got the point 0, 1, and it grows exponentially like that. So we've got to figure out what these transformations there do. Now the -1 moves the entire graph down 1 unit. That's going to affect the horizontal asymptote. So the horizontal asymptote moves down to -1. And that has an equation of y equals -1. Now the y-intercept, remember you find it by letting x equal 0. 0 plus 2 is 2. 2 squared is 4. 4 minus 1 is 3. So the y-intercept is the point 0, 3. And if we choose another point, I'm going to choose, let's choose negative. I'm going to choose -1. If I plug in a -1 for x, for that x in the original function here, -1 plus 2 is 1. 2 to the first power is 2, and 2 minus 1 is 1. So the point -1, 1 is on the graph. If I choose -2 and plug a -2 in for that x, -2 plus 2 is 0. 2 to the 0 power is 1, and 1 minus 1 is 0. So we've got point of -2 comes 0, and this is exponential growth, and we know it's growth because the base here, the base is 2, which is bigger than 1. Any base bigger than 1 is going to have an exponential growth. So there's the graph. Now, question 10 is from section 4.4, solving exponential and logarithmic equations. So the problem here is we've got two logarithms, two separate logarithms. Luckily, they have the same base. They both have a base of 6. The trouble that some students have, most students do a pretty good job of remembering what gets rid of a logarithm. If you want to undo a logarithm, in this case, you would use a base of 6. But see, the problem is you can't use a base 6 here and a base 6 there and a base 6 there. You can only use one base on the left side of an equation and one base on the right side. So this isn't going to work. You can't do those multiple bases. What you need to do is combine this logarithm into one logarithm. So you combine the two logarithms into one logarithm by combining what's inside of them, the x plus 2 and the x minus 3. Now you're either going to multiply those terms or divide them, and the way you decide is looking at what separates the two logarithms. If there's a plus sign separating the two logarithms, then you combine these expressions by multiplying. So it's going to be x plus 2 times x minus 3. Now we've got one logarithm that I can get rid of that one logarithm now by using a base 6 on both sides. So now I've got x plus 2 times x minus 3 equals 6. Another problem students often have is they see this and think, okay, well that's already factored, so my solutions are -2 and +3. Problem with that is the right side doesn't equal 0. That's a problem. So what you're going to have to do is multiply those two together. So that's going to give you x squared minus x minus 6. And then it equals 6. So what you need to do is now get the right side equal to 0 by subtracting 6 on both sides. And you're going to get x squared minus x minus 12 equals 0. And that factors into x minus 4 times x plus 3 equals 0. Now, solution here is x equals 4. And another one here we could consider x equals -3. But the problem with -3 is if I were to plug a -3 in for this x up here, then you would have -3 minus 3, which is -6. You can't take the logarithm of negative values. So -3 is it was called extraneous. It's an extraneous solution. Question 11, we have the same problem. We've got multiple logarithms, and I cannot just use that many bases to cancel them. You can only use, remember, you can only use one base on the left side, one base on the right side. So what we need to do again is condense those two logarithms into a single logarithm. Like I said in the problem above, with these two expressions inside the logarithms, when you condense, you're either going to multiply those or divide those. In this case, there's a minus sign between the two logarithms. If there's a minus sign separating the two logarithms, then you condense by dividing those two terms. So it's going to be 9 divided by x plus 2, and that equals 2. Now that we have a single logarithm, I can cancel that logarithm by using a base of 3, which leaves the equation 9 over x plus 2 equals 9. Now, one way you can solve this is changing 9 into 9 over 1, and this is called a rational equation. And if you have one fraction on the left and one fraction on the right, you can solve that by cross-multiplying. Okay. Or if this way isn't working for you, let me go back to how we had it. The x here is down in the denominator. Don't want to have it there. So earlier in the review on a similar problem, we had to multiply by the denominator on both sides to cancel it. So then we had 9 equals 9x plus 18. You subtract 18 on both sides, you get 9x equals -9. So x equals -1. Now, just because x is negative doesn't mean that it's extraneous. If you were to plug -1 back into the original logarithm there, you get -1 plus 2, which is +1. So that ends up working. Now, I'd pay particular attention to question 12. This is still from section 4.4. Well, 4.4 and 4.5. Solving exponential equations. We didn't actually solve one that looked quite like this. Now, first of all, this e to the 2x is the same thing as e to the power of x squared. Because remember, when you have a power raised to a power, then the two powers just end up multiplying, and 2 times x is 2x. So there's a first little hint. Now, on a separate problem, if I were to ask you to solve x squared plus 5x minus 6, x squared plus 5x minus 6, equals 0. If you were to solve this equation, you would factor it as x plus 6 and x minus 1. Set it equal to 0, and you get x equals -6 and x equals positive 1. That kind of an equation is really easy for you guys. It's just factoring a quadratic. What we need to do, I'm going to separate this because that was just kind of a side note. What we need to do is make this equation look more like that one. You're saying, well, we've got these e's in there. How can we make it look like a simple quadratic? Well, this technique is what's called U substitution. So if I let u equal e to the x, then this e to the x right here could just be a u, and this e to the x there could be a u. So those e to the x's could turn into u's. So what we would have then is, instead of e to the x squared, it would be u squared. And then instead of plus 5e to the x, it would be plus 5u. So now we do have a simple quadratic, which is exactly the same as that quadratic. So we would solve it using factoring u plus 6, u minus 1. So u equals negative 6, and u equals 1. Now remember, u is just e to the x, so now we would change it back into e to the x equals negative 6, and e to the x equals 1. So now we have two small equations to solve. We have to solve them separately. So I'm going to solve this one. E to the x equals negative 6. To get x by itself, you have to cancel a base. And remember, logarithms cancel base. So if I do a natural log, I can cancel the base e on the left, but here we got a problem. Natural log of negative 6 doesn't actually work. You can't take the logarithm of negative values. So that one, or at least that equation, has no solution. And now the other one here, the e to the x equals 1, we can solve that one the same way using a natural log on both sides. So the natural log cancels a base e, and then you get x equals the natural log of 1. If you were to type that into a calculator, natural log of 1 is 0, so x equals 0. Yeah, I think the numbering got a bit off here. It went from question 12 to question 18. So apologize for not keeping track of the numbers there. Now these are chapter 5, Systems of Equations and Inequalities. Both of these questions, 18, well, part A and part B, are from section 5.4, which is solving nonlinear systems of equations. But you have to solve these using two different techniques. One can be solved using elimination. The other one can be solved using substitution. What I mean by that, if I were to try to use elimination here and multiply the bottom equation by -1, I can't cancel an x squared and a 3x, and I can't cancel a y squared and a -y. There's nothing there to eliminate because I don't have like terms. I've got a y squared and a y, or an x squared and a 3x. Those aren't like terms. But on part B, if I were to try to add these equations together, y squared minus y squared is 0. So those terms do eliminate. X squared plus x squared is 2x squared. And 16 plus 2 is 18. So divide by 2. We get x squared equals 9. Take a square root on both sides. And x equals plus or minus 3. Now we've got to solve for y. So if I use this top equation, now I'm plugging in 3. So I've got to do this twice because I've got two different values. So when x equals positive 3, I'm going to get 3 squared plus y squared equals 16. That gives me y squared. Now 3 squared is 9. If you subtract 9 from 16, you get 7. So y equals plus or minus the square root of 7. So what we have there are 2 points. We have positive 3 comma square root of 7, and we have positive 3 comma negative square root of 7. But now we got to do the same thing when x equals negative 3. Now we're going to have negative 3 squared plus y squared equals 16, which is 9 plus y squared equals 16, which means y squared equals 7, and y equals plus or minus square root of 7. So we have another 2 points, negative 3 comma square root of 7, and negative 3 comma negative square root of 7. So we actually have 4 solutions to that nonlinear system of equations. And the reason for that, not that you would need to graph this wasn't part of the curriculum, but x squared plus y squared equals 16 is a circle, and x squared minus y squared equals 2 it's called an ellipse. You can think of it as an oval, so it's kind of an oval shape. So we've got a circle and an oval intersecting 4 different times. So we've got 4 intersection points. Now, like I said, for part A, we can't use elimination method. We're going to have to use substitution. So if I rearrange that bottom equation and subtract it to 3x, that bottom equation is y equals negative 3x. So that expression for y can replace that y. So then the top equation becomes x squared plus negative 3x squared equals 10. So we get x squared plus 9x squared equals 10. And that's 10x squared equals 10. And that's the same as x squared equals 1. If you square root both sides, you get x equals plus or minus 1. Now, when x equals 1, remember we had an equation y equals negative 3x, so now y equals negative 3 times 1, which is negative 3. So one solution is 1 comma negative 3. When x equals negative 1, we have an equation of y equals negative 3 times negative 1, and where I'm getting this y is from this equation here, y equals negative 3x. And that equals positive 3, so we have those two as solutions. Okay, so now we're back to solving linear systems of equations. For this one, if I multiply the top equation by 2, I would get 4x minus 2y equals negative 20. Bottom equation stays the same. Now I can do the elimination method. But I end up with 0 equals 0. You need to remember that means infinitely many solutions. If there are, the directions say if there are infinitely many solutions, then you write the general form of the solution. I called that parameterize. If there are only two variables, x and y, then the convention is to let x equal t. Let me write that again. Let x equal t. So if x equals t, now I'm going to take the top equation, which was 2x minus y equals negative 10. I'm going to let x equal t then. So that top equation becomes 2t instead of 2x minus y equals negative 10. So I want to solve this for y and get y by itself. So if I add a y and then add a 10, I'm going to get y equals 2t plus 10. So I've got x equals t, and I've got y equals 2t plus 10. So then my solution x comma y is really t comma 2t plus 10. Now I'm going to skip over to part C. Part B and part C are pretty much the same. They actually are both going to end up having infinitely many solutions. Part C has three variables. Now, if I'm looking at this middle equation, I notice that x is already missing. So what I'm going to do then is take the top and bottom equation and eliminate x, because what that's going to give me is an equation with a y and a z, and then I can combine that with this equation with a y and a z. So if I take the top equation just as it is, x plus 2y plus 4z equals 3. And if I take the bottom equation and multiply it by negative 1, I'm going to get negative x plus 2z equals positive 7. If I now do elimination, I can eliminate x. 2y plus 0 is 2y. 4z plus 2z is 6z. And that equals 10. So now I can take that middle equation, which already had a y and a z, and then if I multiply that by negative 2, I'm going to get this equation, or this system of equations, where we get 0 equals 0. That means infinitely many solutions. Now that there's three variables, our textbook uses the convention of letting z equal t. So if I go back up a step, here I've got this equation in terms of y. So if I use that equation, y plus 3, instead of y plus 3z, I'm going to call it y plus 3t equals 5. And then if you move the 3t over and subtract, you're going to have negative 3t plus 5. And then one of the original equations was x plus 2y plus 4z equals 3. That was one of the original equations. So I can replace y with a negative 3t plus 5, and I can replace the z with a t, and then combine like terms and solve for x. So the 6t, the negative 6t and the 4t are negative 2t. And if I move the 10 over there, subtract, I'm going to get negative 7. Then if I add the 2t over, I'm going to get x equals 2t minus 7. So I've got z equals t, y equals negative 3t plus 5, and x equals 2t plus 7. So then the general form, instead of x comma y comma z, would be 2t minus 7, negative 3t plus 5, and t. Now remember, the reason for parameterizing or writing the general solution is if there are infinitely many solutions, then this form allows us to come up with as many solutions as we want by letting t equal different values. For example, if t equals 0, then 2 times 0 minus 7 is negative 7, and negative 3t plus 5 would be negative 3 times 0 plus 5, which is 5. So there's one of the solutions, negative 7 comma 5 comma 0. Using that same technique, you can generate any number of solutions by letting t equal different values. Okay, this next question is from chapter 5 still, 5.5. Graph the solution set, label all vertices. The solution set is the area that contains all the shaded regions if we were to graph all of those on the same graph. And the vertices are where the graphs intersect with each other. So we're just going to graph one at a time. This first one here, negative x squared plus 7, is an upside down parabola that's moved up 7 units. If I plug in an x equals 1 for x right there, I'm going to get 1 squared, which is 1, times negative, which is negative 1. Negative 1 plus 7 is 6. So 1 comma 6, which also means negative 1 comma 6 is on the graph. And since it's less than or equal to, it's a solid parabola. Now we've got to figure out where to shade. If I use a test point of 0 comma 0, that means that I'm going to let x and y equals 0, so I end up with a statement that 0 is less than or equal to 7. That's true, so the test point worked, which means that I'm shading where the test point was. So that's inside the parabola. Now the next one, the negative x plus 5, that's a linear inequality. It's in the form y equals mx plus b. So the plus 5 is my y-intercept, and the slope is negative 1. So that means we're going to go down 1 and over 1. And it's also, listen, or equal to. The equal to means this is going to be a solid line. And then we've got to figure out where to shade. I'm going to use the same test point, 0, 0. So that means both x and y are 0. Then we end up with the statement 0 is less than or equal to 5. That's true. So for the line, we're going to shade towards the test point, which is underneath. The test point was underneath, so we're going to shade that because the test point worked. Now, this other inequality, y is greater than 1, if there's no variable and it's just y equals a number, that's a horizontal line going through 1. And since it's just greater than and not greater than or equal to, it's a dotted horizontal line that goes through 1. And since its y is greater than 1, numbers greater than 1 are above, so we're going to shade above the line. So now we've got to really identify and look closely where the triple shaded region is. So I'm going to identify so for shading below the green line, underneath the parabola, and above that dotted line, and that gives us this area right here. That contains all the shades, black, green, and purple or blue. So that would be called the solution set. But now we need to label the vertices. These points here that outline that solution set. So this point here that point is an intersection of that inequality y equals 1 and that inequality y equals negative x squared plus 7. Those are the two graphs that are intersecting to form that point. So one thing I do know is that y is going to equal 1, because it says right there it's on the graph y equals 1. So if y equals 1, and I use this equation now, 1 equals negative x squared plus 7, that's going to give me x squared equals 6, which is x equals plus or minus the square root of 6. Now, since this point is on the left side of the y-axis, I know it's going to be the negative square root of 6. And the nice thing is, this other point directly opposite is on the other side of the parabola. So that's going to just give me the point positive square root, comma 1. Now, this point and that point, both of those points those two points intersect on the same two graphs. It's the parabola and the straight line. So those two intersection points can be found by solving that system. Those are the two equations that involve those 2 points, the parabola and the straight line. So if we solve that system of equations, if this expression is equal to y, and this expression is also equal to y, that means those two expressions are equal to each other, because they both equal y. So I can write negative x squared plus 7 is equal to negative x plus 5. And if I want to get all the terms on the same side, I'm going to move the terms on the left to the right. So 0 equals positive x squared minus x minus 2. That can factor into x minus 2, x plus 1. So we get x equals 2 and x equals negative 1. So I know that this one let me change that here. This one has the x value of positive 2 because it's on the right side of the x-axis, and this one here on the other side has to have the x value of negative 1 because it's on the left side of the y-axis. So when x equals 2, y equals, now I'm going to refer to this expression, it's the opposite of x plus 5, so it's negative 2 plus 5, which is 3. So that's a 0.2 comma 3. When x equals negative 1, we're going to get y equals, I'm going to refer to that again, the opposite of x. X is already negative 1, then the opposite is going to be positive 1 plus 5, which is 6. So that's the point, negative 1 comma 6.